like to have a working group on hierarchy builder. I thought I would give an introduction to hierarchy builder, and part of it will be illustrated on the construction of the Lebesgue measure, just for fun. I will have simpler examples as well. So this is a work where several people contributed in different parts. Some people contributed on hierarchy builder, and some people contributed on measure theory and kind of at the intersection. All of this is in Coq, which has or will be renamed ROC, just to have a bit the confusion here. And to start, I will give a crash course on how to build the Lebesgue measure, but in 4 bullets, I think. But what's important there is to spot the places where some structure appear. So we did a construction based on the Kara-Theodori extension theorem. So the first thing we need to do is to define a pre-measure on intervals. So that's very standard. Where a pre-measure is a function from sets to reals or extended reals. For us, it would be extended reals, which is 0 on the empty set, which is non-negative, and such that the countable the measure of the countable disjoint union is the sum of the measures. And here already there is a small detail, that is the definition of a measure and the pre-measure is not the same whether you are on the semi-ring of sets or on the sigma algebra. So there are already 2 structures that have been introduced here implicitly in this slide, in this first bullet. It's the structure of semi-ring of sets. And the structure of measure, so it's a structure on functions and pre-measure. Then you need to show that this extension of the measure is in fact an outer measure, where outer measure is yet another structure on functions. And then you have Kara-Theodori lemma, which says that this class of sets is actually a sigma algebra on which the restriction of the measure, the outer measure you take, is a measure. So sigma algebra is yet another structure that appears. And then you finish the proof. Oh, I forgot to fix this slide. The Lebesgue measure is mu star, actually, where you restrict this outer measure to this sigma algebra of Kara-Theodori. Do I have a pointer?
You want
There is no pointer.
Oh, I brought my own, sorry.
Oh, thanks.
It's A in item 3. Complement. What is A in item 3?
I guess I forgot the quantification over all A. I should look up the definition in
X is A?
No. For I think it's
There's an A inside the.
yes, there should be an A inside the. It's all X such that for all A. I don't know. I think it's for all A actually.
No, for all A, that's amazing.
No, there is no summary anymore here. It's well, we can look it up later.
It's wrong.
There is in fact a mistake.
Sigma measures are defined on all sets. That's for all A.
Yeah, it's for all A. More questions? So in the end, the restriction of mu star to the Lebesgue measurable, which are the Kara-Theodori set on mu star, is the Lebesgue measure, and it's unique. It's the unique way to extend mu when mu was actually sigma finite. That's what I forgot in this slide. So to sum up, we have semi-ring of sets. We have pre-measure, we have measure, we have outer measure, we have sigma algebra. In fact, the proof will also involve rings of sets and sigma rings of sets, which are intermediate structures between semi-rings of sets, and sigma algebras. And if you start formalizing without all of this in mind, you will have to refactor your code a few dozen times before you reach the right granularity in all the structures you mentioned, and you may have to change some interfaces. And the point of the tool hierarchy builder and this talk is to show you how to avoid unnecessary burden whenever you need to make these tiny adjustments, which would be tiny on paper, but if you encoded a hierarchy yourself using the bare blocks of type theory, then you're going to spend hours moving things around. Does that remind anyone else's experience here? So, yeah, that I said. We also need rings of sets. So, what I mean by a structure is a carrier, constants, and axioms. Actually, as I just said, the carrier could be more than a set. It could be functions, or it can be something else. But I will not detail this here. And a simpler example, and for now and until the middle of this year, I will only deal with monoids and groups and semigroups just for the simplicity's sake, because not everyone's very fluent in measure theory.
There's no such thing as an additive monoid. There's a monoid.
Well, it depends on your point of view.
Well, depends how you denote the operation.
What you call a monoid. If you name the operators, then if you name the low add, then it's an additive monoid. If you have an unnamed structure, then you can say it's just a monoid, but in fact.
Type theory is invariant under renaming.
But we are not.
I agree.
This tool is trying to make the interface between us and type theory. So what we usually do when we write down monoid in mathematics is we name the operator with a concrete name. So what I'm claiming here is if we want to reproduce this practice, then we need named operations, and then inside the type theory, maybe it should be the same, maybe not, but we shouldn't care about it. So just a brief reminder, because I assume...
You forgot to change the rock thing.
Oh, yes! It's not, yeah, that's the problem with talks that have been spending a long time.
So we're not stable through alpha conversion then.
What?
We're not stable through alpha conversion then.
Yeah. Okay, so I don't want to give a comprehensive overview of type theory, but the only thing I will be using anyway is the records. So I am just giving the Coq syntax for rock syntax for records, because it might be slightly different from lins. And I also want to do a small naming convention, not reminder, but the keywords record structures and structures are actually synonyms in Coq, but when I say structure, I really mean structure in the mathematical structure sense, whereas record just means a bunch of data. And the class is also a record, but with special metaprogramming data attached to it that I will detail a bit later. And there are several ways to actually implement what you think is a mathematical structure in dependent type theory, and one of them, I think this was first deployed on a large scale with math classes in this paper, is what is called, or actually now is called unbundled class. So for each representation I will have you can put it on the spectrum of bundling and whether it's a class or a structure. So it's unbundled because the parameters of the class are actually the meaningful content, and the fields are the axioms. So whenever you quantify on this, you need to quantify over T, 0, add, and this class. And it's a class because, well, it's a class. And a class means that any form of inference will be performed on the parameters. Then there is the semi-bundled class approach, where it's still a class because you may perform inference on T, but it's semi-bundled because you still have one parameter and you put the rest as fields. So that's yet another representation. It's the one that's used in Mathlib. A mixture of which is used in Mathlib. Then trouble comes actually when you are defining several structures. So a hierarchy is defined when you have at least one structure, but trouble comes when you have more. And then there are many ways to express inheritance. So this is one way to express inheritance. You can either say this, meaning there is, for example, if you want to show that, if you want to define a group from a monoid, you can say just the contents that is required to extend monoids so that when you add this content, it's a group. And there is so this means that in particular when you quantify on a group in this way, you need to first quantify on a monoid. So in Mathlib, for example, you don't do this for groups and monoids, but you do this for modules and other kind of objects. So you can actually choose between this representation and this one, which is the one saying, I just take back the data I had from monoid, and I inline the contents of it inside my definition of a group. So either you do it verbatim, or you can actually, if you're doing it manually, you can amend it. Because now, when you added those two axioms, this one became spurious. So you could actually define a group with less axioms than the concatenation of the two sets of axioms that you put in monoid and I extend to a group. No questions so far?
So is it still a monoid if you define it this way? Does the type system, no type class system know that it will be a monoid?
Only if you put an instance that, and if your type theory has a definitional proof irrelevant type of propositions, then you don't run into problems. Otherwise you do, but it's not the point of this talk. Or not yet. I can detail that at the end or during a coffee break. Then there is yet another representation, which I call bundled record. So it's not a class anymore. Actually, I should have said bundled structure rather than record. Sorry for that. And you see the difference here with the class is that you decided to put the parameter inside the structure. So now when you quantify on the monoid, you only quantify over one object instead of two.
Is there a relevant difference between record and structure here?
It's just what I said in the beginning. It's just a naming convention. When I say structure, I really mean it should be an element in a hierarchy, whereas a record is maybe an arbitrary bunch of data that's not meant to be part of a hierarchy.
But in Octa, both keywords exist, right?
Both keywords exist and their equivalents.
Okay.
What's that greater than after sort colon greater than?
Yeah. So this in Rock means that you can that you have a implicit coercion from monoid type to type, so that you may use monoid type as if it were a type.
Great. Very nice.
That's one of the facilities that the language may provide you or not.
So sorry, by a hierarchy, you mean actually a sequence of structures that are defined recursively depending on the
Yes. Well, I will come back to that later.
Hopefully a lattice of structures.
Yes,
Oh,
okay, then
yes.
more than just...
Hopefully,
Hopefully also.
hundreds and hundreds and hundreds of them. Not too many, I hope. Okay, so I just want to refine this a little bit more to explain all the possible encodings, because this one is particularly interesting. So I call this the simplified packed class. The packed class, proper packed class will come later. Just to show that the class representation and the structure representation are not incompatible, they're complementary, because you can reuse the definition of a class to define a structure by saying that instead of inlining the class inside the structure, you can just put a field that's saying that there is a copy of it inside. And that's now the time for the packed class representation, which is the one that's used in MathComp since at least 2009, but actually this is the paper from TPHOL describing it, where it's the same principle, except when you have more than one structure, you need to decide how you put everything together. So the first part is the one I said before. You have, I should have said class, but maybe you decide it's, forget about class and records for now. So is monoid is the data you need to define monoid from a type, and monoid type is the packaging of the carrier and this class. And then when you add data, of course you can say I have my extra data and monoid this group is this data, extra data, but then I can bundle together the monoid, what I needed to make a monoid and what I needed to extend it to a group, and then I can put it inside the group type. So this packed class representation is actually the one that regroups all approaches that I said before in one, and you could decide to reuse any parts of it. There are many other implementations you can you could make to represent algebraic structures in dependent type theory. You could use first class modules as they are in Coq, but they are not first class in Coq actually. They are first class in OCaml, but not in Coq, and it means you cannot quantify on a module without making a module, which is actually a very hard constraint to phrase results. So I claim this is not a good idea. You have fully bundled type classes, which you can find in a few Coq developments, but which are inherently bad because fully bundled means you have no parameters left, and parameters is what guides the inference. So you have nothing to guide the inference anymore. So you may find, you will explore the entire universe before you find the right structure, if it's even the right structure in the first place. Then you have telescopes, which is, we can remove records and flatten all arguments as you go, so you can have a set of variables that grows as you delve into deep mathematical results. And then you can use all I said without using any kind of inference, and that's really difficult to handle. So that's why, in addition to what is used in all of these systems, there is an extra layer of metaprogramming. So in Coq MathComp, it's canonical structures that are used to guide to make sure you will find instances or implement inheritance. In Coq math classes, it will be type classes. In MathLib, it's type classes. In Agda, it's directives that are, it's a pretty smart set of directives to be implemented. But it's not all, because all of this is very error-prone. And there is many external tools that have to be added to such libraries in order to check. For example, in MathComp 1, there was a heavy boilerplate. Every time you wrote a structure, you needed to write at first one extra declaration. The second structure, it was two, and I let you imagine how many extra declarations you had to make when you reach the 100th structure in your hierarchy. And we made mistakes, and we needed an external tool to validate that we didn't miss an instance declaration somewhere. In Coq math classes, there is a lot of boilerplate too with hints. In MathLib, there is a clever set of priorities, and you need to know how to organize your type classes so that the inference will not blow up. So there is a linter to perform these checks, but it's heuristic, so it's not complete by definition, and you may still get beaten. And in Agda, as I said, it's a set of opening and renaming directives. So none of those are straightforward. You need expert knowledge for all of this. And some encodings are unnecessarily verbose, unnecessarily mean for end user. It looks like it's spurious. And some design problems might be detected too late. I can give more details upon request on that. And refactoring takes a long time. I've heard that there was a refactoring of structures in MathLib these days, or planned, about set-like and fun-like.
We're always refactoring this.
Okay, so how much time person does it take?
These are long jobs.
So what I claim is if you have an extra layer to insulate you from this job, then you might port what you did to hierarchy builder once, and then if you need a redesign of your infrastructure, you can change the way hierarchy builder will represent this in type theory so that you don't have to change your visible declarations. So what do you need when you have a hierarchy? If you want to build a hierarchy, you need to be able to factor theorems and automatically find which structures are equipped on which types. And so you need to be able to declare new instances, and you need to be able to declare new structures. Sometimes it will be extensions on the very top. You're defining a new structure that is more specific than any structure you had before, but sometimes you're defining a structure that's somewhere in between two other structures. And that's where refactoring comes and bites you. And you need to be able to handle various joins in your hierarchy. Sometimes you define structures that go in different directions and they join again to form a new structure, sometimes with extra axioms, sometimes without. And when you do all that, you need to maybe change the code, or maybe you wrote, or maybe you need to you can write it out of the library. It's not too invasive. You also need to provide several ways to instantiate objects, because sometimes when you want to prove something is a field, maybe you don't want to prove that it's a commutative group, and then it's a group, then it's commutative, and so on and so forth. Maybe you want to have a bulk way to get that. You need predictability of the inferred instance, because if you don't know which object the inference returns, you're in a mess. And you need robustness of user code with regard to new declaration, meaning that any introduction of a new instance shouldn't break anything. Any introduction of a new structure shouldn't break anything, meaning that if your interfaces change, you should be able to have a seamless change everywhere else. So that's the job of hierarchy builder. It will provide a minimal language to generate a hierarchy from the inputs well, at least I think it's minimal to do that. And it lets you amend an existing hierarchy and rewrite a code at the very bottom of your hierarchy in a way that will not break code that doesn't directly depend on the change. So if you're changing the definition of a group, it shouldn't change the definition, whatever you wrote about schemes or whatever objects I don't really understand. So the point of view is that hierarchy builder is compiling to type theories, regarding type theory as a language that is used to represent mathematics, but is not the language you want to see all the time. So some expressions are fine, some should be kept hidden. Concretely, the way it works is it compiles right now in Rock. It will compile to the methodology that was already in mathematical components, which means we could actually update the whole mathematical components with it without much effort. We enforce a discipline that I will explain right now, and it includes built-in safety measures. So you don't need a linter anymore for many checks that used to be performed. They can be performed at declaration time by, since the tool has the representation of the hierarchy, it can check whether the new structure you are inserting is actually not breaking guarantees that we know should be preserved by the addition of a new structure. In order to explain the discipline that hierarchy builder enforces, I have 10 minutes left.
Yes.
Okay, so I will try to make it short. There is this tension when you define, when you introduce mathematical structures especially in education, between whether you define it by extension. For example, monoids, you often define groups using monoids, and rings using groups, and fields using rings. But for other structures, you actually don't define the more general ones before you define other ones. Like norm space, you never say a norm space is actually a uniform space, and a topological space, and a metric space, and before saying it's a norm space. But I guess it's the case in MathComp, and it's the case in Lean, that actually a norm space includes all of these for the good behavior of the inference. So the problem is going through those arrows should be automated, and they are not all meaning exactly the same thing, and there is a tension between extending and entailment, and you cannot say it will use one or the other, because hierarchies actually use structures that come from either way of viewing objects. So the problem with this is that there are problems with the two approaches. So when you do structure extensions, you don't need to start from scratch all the time, so that's good. But it's noisy because you may have extra axioms, as I said before, and it's not robust because when you add a new structure, it means you have to rewrite everything. Structural entailment is flexible on the other hand, so you don't need to cut structures by hand into small bits, and it's, if you need to instantiate something, you can do it in one go, no need to go through the whole chain. And it's robust because you can fix operations and axioms once for all, and you know it won't change because you know that when you add a new structure, you won't cut the pieces and scatter them.
Sorry, what do you mean by entailment? I didn't get that.
I mean, like, a norm space is a metric space because you can define distance from the. But this step is the problematic one because it breaks inference when you create data like this. So the solution is to get the best of both worlds and have internally a system that works solely by extension, but provide an interface to handle entailment in a way that is readable. And it leads to those 5 primitives, and I will give an example of them. So the first one is mixing. You can view it as a primitive interface. The second one is a factory, which is a fake interface. Well, fake for the internal of the system, but it's a true interface for any user. So any external user shouldn't distinguish between mixins and factories, which are both interfaces. Builders are ways for the developers of the hierarchy to say what the fake interface mean in terms of primitive interfaces, in terms of mixins. Then structures can be defined using either of mixins and factories because there is an invariance on whether you pick one or the other. And instances can name either mixins or factories because you don't need to rely on their status internally. For example, if you take this definition of a monoid, so you can say a monoid is this data attached to a type M, and you can build the structure M of monoid by saying it's the structure of with M, which is to which I attach the data that correspond to is monoid. Then I can instantiate the integers on the monoid by using this data and feeding all the fields. So I provide the 0, the add, the associativity, the left neutrality, and the right neutrality. And that will instantiate, that will make sure that Z can be type checked as a monoid later on. But now if I add a structure below, a structure of semigroup, then I need to cut into pieces. And the two pieces will be the semigroup 1 and what I need to extend the monoid from a semigroup. And when I do that, I break the code I have, so it's not robust anymore. And the way to fix it is to introduce a factory with the same name as before, for which I explain how to split it into two pieces, one as a semigroup and the other one as the piece that are required to extend the semigroup into a monoid. And I can reuse exactly the same instance as before. The system will compile it down to the new infrastructure without me knowing. And that's what makes sure I can amend the hierarchy and preserve robustness. Yes?
That was 5 minutes, but also,
5
since I'm at it, so you're starting from big things and showing how to break them down?
Yeah.
Huh.
So there is the mathematics, we sometimes overcome this problem by using duality. So for example, you have the duality between Boolean algebras and topological spaces, and growing Boolean algebras corresponds by the duality to going down in the topological space. So this entailment by duality would be the dual of what did you call the other one? Building, or you had two slides, the slides entailment and what was the building up and going down. Does this idea come at all in your works, where the structures that actually entail are just the duals of the structures that grow up?
I don't see a connection right now, but maybe we can talk about it.
So hierarchy building, how about the integers for that?
No, it's just as an example.
Okay, so that HB.instance.
It's an example of instantiation of the hierarchy. So it doesn't need to know about it, but if you want to inhabit the structures in your hierarchy, you can by using an instance.
So many instances will also just be in the ordinary library and not in hierarchy builder.
But this is in the ordinary level.
So this is the way to build a hierarchy using hierarchy builder. I didn't show you how hierarchy builder internally works. I'm showing you how to use it to build a library. So this is a tiny toy library, but it's been deployed on MathComp, and you have at some point structures like this, and you provide instances in the library where you define the hierarchy.
Oh, I thought there was like one canonical repository containing.
No, hierarchy builder is just a tool. You don't have hierarchies. You can use it in your own repo.
I thought one of the goals was to have sort of one canonical hierarchy that multiple proof systems then export into their own.
Oh, that's a very interesting idea. Maybe we can talk about it.
Okay.
This is something you can do faster.
Yeah. No, I thought it was part of the stuff already.
Yes.
Anyway, continue.
But I guess, so when you define you have to use HB to define the instance.
Yes.
You cannot use Coq's regular instance command.
Well, you should not.
You should not, because
should not.
it would break your properties.
Yeah, it would break all the invariants that hierarchy builder strives to enforce. Yes.
I just wanted to comment, this looks like a lot like locales in Isabelle.
What is like locals in Isabelle?
Well, in the simplest form, it is a localized context. When you can nest them, you can introduce types and constants and axioms. You can build on top of them, but also if you have two locales and you can show that one can be interpreted in the other, then you can also get a kind of an inheritance relation that way, although there's no direct inheritance by construction, you can prove inheritance by showing that there is an interpretation of one into the other. You can pile these very high, and then if you open one and work in one, you have all that context is implicitly available.
So I guess this is almost, if not exactly, the same kind of behavior. Yeah.
There's a huge difference, which is that structures are inferred at the point of use. You don't
Yes, that's true.
You don't need to open anything.
Yes,
You just use things and
that's the
it works.
difference.
And of course, a lot of these things are going to look like, because they're all present in the semantics of type theory, right? A lot of these things are true in the category of context. And all of you've got pullbacks, like a lot of these things semantically are very clear. And the difference between them are all those issues of pragmatics. How does it work in system X? And how does the tooling make it much nicer in system X?
Just to apply it to measure theory, here measurable spaces, if you start with the measure theory, all you learn about usually is sigma algebras. So you make a measurable space out of a sigma algebra by saying that you have a set of sets that satisfies well, sometimes it's stable under countable union and intersection and complement. Here it's a slightly different one, but as I said, you could provide an alternative interface that reduces to this one, where you say it's stable under countable union and complements instead. And at some point, when you try to build the Lebesgue measure by extension, by the Carré-Theodoric extension theorem, you realize that you need some rings of sets and rings of sets, so you can just decide now that this old interface was a factory. You explain how it will be compiled down to the other building blocks, and Mario.
What's this short attribute?
Let's talk about it later. Shouldn't have put it. And then you can add the other building blocks, and since you show how everything reduces to those building blocks, you're okay, and you didn't lose your previous interfaces, so everything that depended on it is safe. For measures and contents, you can do the same. So you can define a content, and you can say, so a content is almost a measure, except it's not sigma additive, it's only additive, so finitely additive, so it's mu of finite disjoint intersection is the sum, the finite sum of the parts. You can see it, so you can define a measure as an extension of the content with the sigma additivity, except now it's a bit too strong to instantiate, so you can provide an extra interface, that I didn't show, so you can provide an extra interface to say, I just need sigma additivity, and sigma additivity implies additivity. And here you can see it's semi-additive and semi-sigma additive because it's a semi-ring of sets. And on semi-ring of sets, things are slightly different, but on rings of sets, you recover the usual interface. Which is, the funny thing, it's, I mean, that's something I said about measures and pre-measure. Actually, in the literature, both exist, but they're actually the same, except pre-measures are always well defined if you, as soon as you have a semi-ring of sets, whereas when you look at them on the, not a ring of sets, but on a sigma ring of sets, then they become the same as measures. So actually only one definition is required with a theory that will depend on whether you have enough objects in your set of sets. You can also notice that, I mean, I didn't know this fact, but it happens to be useful at some point, and I thought it was interesting to get it as part of all these juggling pieces in measure theory. You can show that a measure that is sigma subadditive on a semi-ring of sets is in fact a pre-measure. I think I forgot the hypothesis.
That's
You should-
very
you should-
important.
it should be non-negative.
You need to wrap it up, so maybe this
Oh, and that doesn't matter. The implementation is for later, and you should use it because it's easy to use, it's predictable, it decorrelates the knowledge between what you know and what the system knows, because factories can provide you simplified interfaces. It's robust with regard to changes, and you can change the backend without changing your library.